Yeah, so this is being recorded now and present now. Your entire screen, share. Can you see the PowerPoint slide?
Yes, sir.
Okay. Okay, so I'm starting then. Hello everyone present here. So this is basically about the course of river engineering, and I'm going to discuss the assignment 0. This river engineering course is an NPTEL course in collaboration with the scheme, and the course will be tutored by Professor Subhashish Datta from the Department of Civil Engineering at IIT Guwahati. And I Abhishek Chakraborty, am one of the TAs for this course. I am a PhD student under the Prime Minister's Research Fellowship Scheme at the Interdisciplinary Center for Water Research, ICWR at IISc Bangalore. So the first question in assignment 0 was about the unit of specific energy. Specific energy, we know it is basically nothing but the total energy at a section with respect to the channel bed as datum. We have already learned it from our previous classes on fluid mechanics as well as open channel flow. So just giving a brief recap of it. Let us suppose I'm drawing a channel bed. So this is the channel bed. This is the free surface level or the water level. Okay. So one of the heads, if we take the channel bed as a datum, then we will get number one y, that is the head due to the standing water, and the velocity head. The velocity head can be written as alpha times v square by 2g. This dotted line is the total energy line, and this one is the channel bed. Okay. So the specific energy, which I am writing here as E, is nothing but the sum of these two quantities, y, that is the water level depth, plus alpha times v square by 2g, that is the kinetic energy head. Now alpha is nothing but the kinetic energy correction factor. We know that for river flow, or in general for open channel flow, mostly the turbulent flows exist, and for turbulent flows, alpha tends to be nearly equal to 1. So we can straight away assume that E is equal to y plus v square by 2g for our analysis. And since the specific energy is nothing but the summation of two depth-based entities, so the unit of this specific energy should also be uh, a depth-based entity, that is meters. So the answer to this question uh, should be option B. Option B is the correct answer. So moving to the before moving to the second question, I will just give you a brief recap about brief recap about it. For it, I would be needing another slide. Yeah, that should be okay. So, there is something known as the specific energy curve, which is nothing but the curve between E, that is the specific energy, versus the water depth, that is the Y. Y is on the ordinate, that is on the Y axis, and E is on the abscissa for this curve. Let us just take an open channel flow with a cross section as rectangular. Let us suppose y is its water depth and b is the width of that cross section. So we can write the specific energy as the summation of the water depth to that of the velocity head, right? Okay. So we can also write the velocity as the as q times q by a, that is the ratio between the discharge to the cross section, right?
Yes, sir.
Yeah. So E can be written as uh, finally y plus q square by 2 ga square, and when we substitute a equal to b times y, as in the case of a rectangular open channel, we can write E equal to y plus q square by 2g times b square y square. It's very simple to understand, right? Now making the specific energy curve, which I told was between y and e. So this is the basic formulation we want to plot for this specific energy curve. We know that there are two entities. Number one, if y tends to 0, then this e will tend to infinity. Similarly, if y will tend to infinity, then e will tend to y. And we also know that q increases, then y will also increase. So using this, we can make this plot like this between for the specific energy curve. Let us suppose this is the 45-degree line. The specific energy curve for different discharges can be plotted like this. This is for discharge Q1, this is for discharge Q2, where Q2 is greater than Q1. Okay, and this is the E equal to Y line. So effectively, these are cubic. This equation is cubic in nature. Now, this is the brief recap I wanted to give you before moving into the next question. The next question is about the condition. At what condition the flow becomes subcritical in terms of flow Froude number? So it is again a very basic question from your previous classes of fluid mechanics. So we know that the Froude number, whenever it becomes less than 1, it becomes subcritical. So the answer is supposed to be option C. Now, some basics about the Froude number. Froude number basically describes the flow regimes of open channel flow. It is nothing but the ratio of inertial to gravitational forces. Now, gravity force. If let us suppose it's gravity, Fg is gravity force. It would tend to move the particle downwards. Whereas inertial force, let us denote it using Fi, it will indicate whether the particle is willing to move downhill, or the heaviness of the particle is represented by the inertial force. So the Froude's number is the ratio of the flow velocity to square root of g, that is acceleration due to gravity, into the hydraulic depth. D is the hydraulic depth, and D can also be represented as the ratio of the cross sectional area to the top width of that open channel. Okay, so we can demarcate FR, the Froude number, into three different classes. If the Froude number is less than 1, it's subcritical. If Froude number is equal to 1, then it is critical flow. And if the Froude number is increasing is more than 1, then it is a critical flow. Now, this subcritical flow can also be called as slow or a tranquil flow, whereas the supercritical flow can also be called as fast or rapid flow. Now, looking at this Froude number, it is basically a ratio of two different entities. So the denominator here, the denominator square root of g times d, can also be taken as the speed of a small wave on the water surface related to the speed of water, which can be termed as the wave celerity. At critical flow, at critical flow, the wave celerity is equal to the flow celerity, right? So this can be represented as Fr, can also be represented as V by C, where C is the wave celerity. Okay, at critical flow, the celerity will be equal to the flow velocity. That is, any disturbance to the surface will remain stationary. In that case, at subcritical flow, flow is controlled from a downstream point and information is transmitted upstream. And at subcritical flow, you will observe backwater effects. And at supercritical flow, the supercritical flows are controlled upstream and disturbances are transmitted downstream. So effectively, the critical flow is an unstable entity. Uh, I will represent it in the next slide. So critical flows are basically unstable. So and when the water depth is less than the critical depth, that represented here as YC, then we will observe supercritical state. That is high energy state. And when the water depth is greater than YC, that is a critical flow depth, then it is a subcritical state. I will explain why is it so. Which is subcritical is a lower energy state. So now when we move back to question number one, I had drawn a specific energy curve in that. Uh, Let me draw that curve only for a constant discharge Q. So that curve will look like this. Q is constant. The minimum energy on that curve will be the critical energy, and the depth corresponding to that will be the critical depth. And for the same energy, you will observe two different same specific energy, you will observe two different depths, y1 and y2, right? These two are the alternate depths. Now just again writing the same expression, y e is equal to y plus q square by 2g a square. We want to find out the minimum energy E at a constant Q. So for that we can take the first derivative of this term. D by dy can be taken as 0. Let me take any cross section, not just the rectangular one. So this cross section can be seen like this. Let me take an elementary infinitesimal strip over it. This is the datum, which is the channel bed in our case. This is the water depth, an incremental depth dy. T is the top width and dA is the infinitesimally small cross section. So dA by dy is nothing but the top width. So now moving into this, the next step for it would be d by dy equal to, we are just derivating this expression. dA by dy can be written as 1 plus q square by 2g. Since q and g are both constant, so we can take them out. Minus 2 by aq dA by dy equal to 0, right? So from here we get 1 minus q square t by g a cube equal to 0. This implies q square t by g a cube is equal to 1. This gives q square by a square times t by g times a equal to 1. And q by a is nothing but the flow velocity v square t by ga equal to 1. Let me just take a square root of it. We will get v square by square root of g times a by t equal to 1. And this is nothing but the Froude's number. So Froude's number should be 1 for minimum specific energy, right? Because a by t is nothing but the hydraulic depth d. So we can say with certainty that whenever the specific energy is minimum for a given discharge q, the flow depth is critical. This is the derivation for that. Now moving into the third question. The third question is the average width of Ganga river at Patna is 1.5 kilometers and the average flow depth is 15 meter. A physical scale model of 1 by 100 scale needs to be developed. The width and depth of the model are okay. So it is basically a problem of geometric similarity. We can just plot the cross section, and here they have taken it to be rectangular, so we will just do the same. The width of the channel Ganga river at Patna is 1.5 kilometer, which is nothing but 1500 meters, which is the prototype. So BP is the notation I'm using for it. The depth is 15 meter, which is the depth of the prototype, so I'm using the notation DP. And scale is given as 1 by 100. From our previous classes of fluid mechanics, we know that scale is nothing but the ratio of the model dimension to that of the prototype dimension. Okay, so the model width can be represented as the scale multiplied by the prototype width, which is 1 by 100 into 1500 meters equal to 15 meters. And the model depth is again 1 by 100 into dp, 1 by 100 into 15 meters equal to 0.15 meter equal to 15 centimeter. So the answer should be 15 meter and 15 centimeter. Answer is B. Now moving to the next question. Uh, as given in question 3, the average flow velocity is 2 meters per second. Estimate the discharge and flow Froude number. Okay, so we have been given the velocity as 2 meter per second. We need the discharge. Discharge is straight away. I mean, straight away we can find the discharge as the product of the cross sectional area to that of the flow velocity. So this is nothing but the cross sectional area is nothing but the product of the width and the depth d times v. Okay, so this is 15 meters times 1500 meters times the velocity. So q will be from calculation 45,000 meter cube per second. The Froude's number we know is the ratio of the velocity to g times d. which is V by square root of G times A by T. Hydraulic depth can be represented as the ratio of the cross-sectional area to that of the top width. T here is 1500 meters, the top width, which is equal to the bottom width because it's a rectangular channel. A here is 1500 meters times 15 meters. This implies D is equal to A by T equal to 1500 times 15 by 1500 equal to 15 meters. So the Froude's number is V 2 meter per second times 9.81 meter per second square times 15, the hydraulic depth, meter per second. So this would be 0.1648, nearly equal to 0.165, which is nothing but option C. So C is the correct answer for it. Next question is based on Froude number similitude and data given in questions 3 and 4. The discharge requirement for conducting the physical model is okay. So this question is about the dynamic similitude theory. Before proceeding into the answers, I will give a brief recap about model theory. Model theory can be used to prepare the models from a prototype. Let us suppose you want to model the spillway over a dam. So how would you build a physical model for it in your own lab? You would be trying to build a flow over a spillway at lab using certain uh, physics based laws. So these laws for model theory are what I'm going to discuss now. So there are three different types of similarities between the model and the prototypes, which we need to ensure while preparing the model. So these similarities can be number one, geometric. So in geometric similarity, we ensure that the model is a geometric replica of the prototype. So the length of the model LM and length of the prototype LP should be similar. And this similarity is ensured using the length scale of the model, here represented using LR, which is nothing but LM by LP. We ensure that for all the dimensions, we keep the length scale to be constant. So this is what we call as geometric similarity. However, ensuring the geometric similarity is not possible always. For example, when we are trying to model a river, we know that the width and the depth are much smaller than its length. So for that, we would usually distorted models are used in which we use a different length scale for the depth and the width than that of the length, because the length is too large of rivers than the other two dimensions. So this was about the first similarity. The second similarity is kinematic one. The kinematic similarity is the similarity of motion, that is either that of the acceleration or velocity along the x, y, and z components. So this length scale, the ratio for the velocity, the ratio for the velocity can be represented as the velocity of the model to the velocity of the prototype. Now we know that the velocity of the model can be taken as the length of the model to that of the time model. Similarly, Vp can be represented as Lp by Tp. Okay, so Vr is nothing but Vm by Vp equal to Lm by Tm times Tp by Lp equal to Lm by Lp times Tp by Tm. So this implies that this velocity scale ratio is nothing but the length scale ratio times time scale ratio, where the time scale ratio, as it was not earlier illustrated, is nothing but the ratio of the time taken by the model to that of the prototype. Similarly, for the acceleration scale ratio, we can illustrate it like this: the model acceleration is Vm, the velocity of the model, to the time by model, equal to the velocity scale ratio times the velocity of the prototype by the time scale ratio into the time of the prototype, equal to Vr by Tr times acceleration of the prototype, which is nothing but acceleration scale ratio into the acceleration of the prototype. So from this we can get that AR is equal to again VR by TR, right? If it is nothing but LR, since VR is LR by TR, so it is LR by TR square. So this is the expression we'll be using mostly for acceleration scale ratio. There is another kind of similitude that is known as a dynamic similitude. I will be explaining it using another slide. Yeah. So the third type of similitude is the dynamic similitude, which would be used in this problem too. Dynamic similarity. So this ensures that there is a similarity of forces. So for it we use a force scale Fr, which is nothing but of the model to that of the prototype, and we ensure that it is constant between the model and the prototype for each of the forces. So let us suppose the inertial force Fi of the model, inertial force ratios between the model and prototype should be equal to the gravity force ratio between the model and the prototype, which should be equal to the viscous flow ratio between the model and the prototype. Fe is the viscous force, right? So for Froude's number, we know that it's the ratio of the inertia to the gravity forces. So uh, we can take these two entities and we can express it as this. Okay. So the inertial force is nothing but mass times acceleration from our classes of Newtonian physics. So mass can be represented as density times the volume, and acceleration can be written in the dimensions of LT minus 2. The gravity force is nothing but the gravity force specific weight times the volume. Specific weight is the product of the density times the acceleration due to gravity times L3. Now, when we put these two expressions in equation star marked star, we will get the suffixes m and p correspond to the model and the prototype respectively. So from this expression we get square by Lm equal to G dp square by Lp. I'm not cancelling G because we are going to finally use it for the expression of the Froude's number. Now, the v, the velocity, is nothing but the length by t. So time can be represented as L by v. Just substitute into this expression, we get G Lm square by Vm square Lm equal to G Lp square by Vp square Lp. Just inversing this equation, we get finally Vm square by GLm is equal to Vp square by GLp. Now, I would need another slide to finally give an expression for this dimension, for the discharge of the uh, open channel as per the Froude similarity. So the last expression we used was Vm square by GLm equal to Vp square by GLp. Just taking a square root, we know that, if we take a square root, we will get Vm by square root of GLm equal to Vp by square root of GLp. This is nothing but Fm, the Froude number for the model, is equal to the Froude number of the prototype. Hence, for open channel flow, if in case we are going to uh, produce a model, we need to ensure that the Froude number of the model and the prototypes are similar. Not similar, same. Now, for Froude models, from this expression, we can write VR by square root of GLR equal to 1. This implies VR is equal to, sorry, this would be VR by square root of LR equal to 1. So from it we can get VR, the velocity scale ratio is length scale ratio to the power half. Now for any physical variable A, let us suppose the physical variable A can be written in terms of dimensions L, M and T like this. This is from our understanding of the dimensionless analysis. So the length, the scale ratio for AR would be finally nothing but the length scale ratio to the power x, mass scale ratio to the power y, time scale ratio to the power z. And the mass scale ratio is nothing but the density scale ratio times the volume scale ratio, which is LR power q power 3. And since rho r is nothing but rho m by rho p, so we can take it as 1, because in case they are the model as well as the prototype are made up of the same material, so the rho r will be equal to 1. This implies mr equal to lrq. The time scale ratio can be represented as length scale ratio to the velocity scale ratio. This is LR by LR to the power 1 by 2, taken from our initial expression uh, for Froude's number, which is nothing but LR to the power half. So AR, the scale ratio for this physical variable A, can be represented as LR power X times LR power 3y, because the mass scale ratio is LR to power 3 times LR power Z by 2, because the time scale ratio is LR to power 1 by 2. This gives us the scale ratio for A as LR to the power X plus 3y plus Z by 2. I would need another slide to finally give an expression for the discharge. So for discharge, which was actually asked in the question, discharge QR, the scale ratio for the discharge is AR. Discharge is nothing but the product of the cross sectional area to that of the flow velocity. AR times VR. A is LR to power 2, and VR from Froude similarity is LR to the power 1 by 2. So this gives us QR to be equal to LR to the power 5 by 2. So moving to the question finally. Based on Froude number similitude and data given in questions 3 and 4, the discharge requirement for conducting the physical model is. So they are asking the discharge. So QR is nothing but the discharge for the model to the discharge of the prototype. This implies the discharge for the model can be represented as QR times QP, and so this ratio is 1 by 100 as it was given in the previous question to the power 5 by 2, LR to the power 5 by 2, and the discharge of the prototype was found to be 45,000 meter cube per second from the previous question. It is nothing but 0.45 meter cube per second. That's the answer. Now moving into the next question. At Farakka Barrage, the water from the Ganga river is directed to a feeder channel. The discharge is 2000 meter cube per second. Estimate the total annual volume of the diverted water in million meter cube. So Q is given as 2000 meter cube per second. The question basically just want you to the question just wants you to convert the unit from meter cube per second to million meter cube per year. So this is what you want to do somehow. So uh, for 1 second, for 1 second, the discharge would be or the volume would be 2000 meter cube as per the question. So for 1 year, it would be the number of seconds in that year, that is 365 number of days into per day there are 24 hours, per hour there are 60 minutes, and per minute there are 60 seconds times the discharge. This comes out to be 6.3072 into 10 power 10 meter cube per year, and just divided by 10 power 6, because the final question, I mean the solution wants, I mean the problem wants it, the problem is to be reported in million meters cube, so just divided by 10 power 6 to get uh, a final solution in million meters cube, and this would be 63072 million meter cube per year. So the answer is D. Question number 7. The sediment concentration at the Farakka barrage is 300 milligram per liter, and the average discharge is 3000 meter cube per second. The total daily sediment load in terms of tons per day is okay. So it is basically nothing but multiplication of these two entities will give us the final answer. So the sediment concentration is 300 milligram per liter, discharge is 3000 meter cube per second. Just multiply these two things to get the final answer. Now the thing is that the units are not consistent, so we need to firstly make the units consistent. They want the answer to be in tons per day. So 1 ton we know is equal to 1000 kg. So firstly convert this 300 milligram into tons. So 300 into 10 power minus 3 will give us grams, into 10 power minus 3 will give us kilograms, into 10 power minus 3 will give us tons. So this thing is done now. Into 3000 meter cube. So 1 meter cube is equal to 1000 liter. So multiply by 10 to the power 3 again to convert it into liters, divided by liter. Okay, so per day they want, so we have to again multiply it using I mean we have to convert per second into per day. So for each day there are 24 hours, and for each hour there are 60 minutes, and for each minute there are 60 seconds. So the final answer will come out to be 77760 tons per day. So this is option number B. This is option number B. That's the answer. This question asks that, as given in question number 7, if sediment trap efficiency is 80%, the average daily sediment deposition at the Farakka barrage is okay. So sediment trap efficiency is 80%. So that means that out of X amount of sediment, 0.8 times X will stay in the Farakka barrage itself. So we just need to multiply the Q from the last answer, that is 77760 into 0.8. So the answer is straightforward, 0.8 times 77760 tons per day, which comes out to be 62208 tons per day, which is option number A. What is the approximate flow Reynolds number of a river? So for rivers, the turbulent forces dominate. We know that very well. And if the turbulent forces dominate, the Reynolds number has to be very high. And from experimental evidence, it has been found that the Reynolds number needs to be greater than 20,000 at least for for a river. So the answer is C. Final question: why does a river meander? So before that, I would just want to show you the rivers. Okay, so basically the rivers flow. I mean, whenever they flow over gently sloping ground, they begin to curve back and forth, which is nothing but termed as meandering in technical terms. So such rivers erode the sediments from the outer curve of each bend and deposit it on the inner curve further downstream, making the meanders grow further in time. So due to this, uh, the correct answer should be option C, that is increasing sediment transport. Just one more thing to be noted here is that the meandering of the rivers, they may increase over time. They may so will they increase forever? No, that doesn't happen. Why? Because after some time, as the meandering has increased a lot, a part of it will be cut off, like this. And that cut off part is what they call as what is known as an oxbow lake. So as soon as a part of that meandering river is cut off as a lake, as an oxbow lake, this process will again continue. So this is the basic of this river meandering. I think I'm done with all the questions. Uh, is there anything you want to ask?
No, sir.
Okay, then I shall finish this session. Thanks a lot. Thanks a lot for joining.